I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on direct current circuits, resistors in series and parallel. In this video, we're going to talk about direct current circuits, resistors in series and parallel. So let's review some schema for our schematic diagrams. So first, if we look at a battery, we know a battery is a long line and a short line, with that long line representing the positive end of the battery and the short line the negative end of the battery. Our wires are just straight lines with right angles. Resistors, any kind of resistors that look like this, or a light bulb, is just a zigzag line. We have a voltmeter, that's a circle with a V in it, and that would measure the potential drop that have to be set up in parallel across a battery or a resistor. An ammeter is just a circle with an A in it, and that needs to be set up in series with a resistor that we're measuring the current that's running through it. We also have capacitors that have parallel lines or a line with a curved line. And we're also going to talk about adding a switch into our circuit, which is just going to be a switch like this. When it's open, no current goes through it. When it's closed, this current will flow through that portion of the circuit. So in a series circuit, we'll start with a battery and two light bulbs that are hooked up in series. Connect the wires, those light bulbs will come on. We'll assign the value of the resistance of R1 and R2. So let's say they have different resistance. So let's draw a schematic diagram for that with R1 and R2 set up in series. And now let's look at the current as it flows through the circuit and the change in potential as it goes through the circuit. When we go through the battery, the current increases in potential. So we'll say VB for potential of the battery. As it goes through the resistor, it drops potential as it's moving from positive to negative. Remember, potential drops as it goes from positive to negative. So minus VR1 and then minus VR2 as it goes through. And then once it gets all the way back to where it started, we know the change in potential is going to be 0. So the change in potential equation would just be the potential of the battery minus the two resistors, and that's going to equal 0. And we can substitute using Ohm's law that the current, since it's a series circuit, we know the current's the same, and then multiplied by the individual resistors. So we can rearrange this equation to solve for the potential across the battery. But that's also equal to the change of the potential drop for each of the resistors, which is also, using Ohm's law, equal to the total current times the equivalent resistance. We know the currents are the same, so it leaves us with an equation of the equivalent resistance is just the sum of the two resistors, which is the way we find the equivalent resistance in a series circuit. So we just sum all the individual resistors if they are in series. So in a parallel circuit, we have a battery and two bulbs again, and we'll label those bulbs again R1 and R2. So we're going to connect those bulbs to the battery, and then we'll connect two more wires in parallel like we did in the previous video with capacitors, and we can see that both of the bulbs are lit. So let's draw a schematic diagram, the battery with the wires. Now this time the branch is going to split where we have R1 and R2, which means that the current is going to split as well. So the current has two different paths, unlike in a series circuit where it only has one path to go. Then we'll continue and finish our circuit drawing the wires. So we're going to look at two charges to represent the current flowing through the circuit. It goes through the battery, increases in potential. When it gets to the junction, it splits and then comes back together. And then it continues on back to the beginning of the battery. So if we write an equation for the total current, we know the total current's going through the battery. But when it gets to this point, it splits between R1 and R2. So the sum of the currents is going to equal the total current that's flowing through the battery. So each of the individual resistors has less than the total current that's going through the battery. And if we use Ohm's law, I equals delta V over R, and substitute in that delta V divided by the equivalent resistance is going to equal the delta V1 over R1 plus delta V2 over R2. Well, what we know in a parallel circuit is that the potential across each resistor is going to be the same as the potential across the battery, so we can cancel those out. And if those are all equal, we cancel them out. We end up with 1 over the equivalent resistance equals the sum of the inverse of each of the individual resistors. which is our equation for finding the equivalent resistance in parallel, is 1 over Req equals the sum of the inverse of the individual resistors. So in series, the equivalent resistance in series, the comma S, equals the sum of the individual resistors. You just add R1 and R2. In parallel, we have the inverse of them, so we'd have to do 1 over R1 plus 1 over R2, which gives us the inverse of the equivalent resistance. So we have to flip it to find the value of the equivalent resistance in parallel. So let's look at Kirchhoff's rules. Kirchhoff has two rules. The junction rule, which applies to parallel circuits, is as current enters a junction, the sum of the current that enters the junction is equal to the sum of the current exiting the junction. So if we have a current flowing through a portion of a circuit, we have I1, and once it gets to the branch, it splits, so I2 plus I3 is going to equal the I1, and it comes back together. So this would be a junction rule equation where we take the currents coming in equaling the sum of the current in each of the branches as the current splits. And this is conservation of charge because the charge that enters the branch that splits has to equal the charge coming back out of the branch, or the charge in each branch as it's flowing through the circuit. Now, Kirchhoff's other rule for circuits is the loop rule. The algebraic sum of the measured potential differences across all elements in a closed loop in a circuit is 0, which we already know from our electric fields video, but we're going to look at it as in a circuit. So if we have this circuit where we've got two parallel resistors and one in series, and I've marked some points, and we look at the loop that goes from A through the CD branch and then back to A, and we measure the potential across anything that would change. So across the battery, we know that from A to B, that's going to be an increase of potential. So we'll take VAB. Across any resistor, it's going to be a decrease. So we're going to subtract the potential across CD, and then we measure it across GH and subtract it, and we know that's going to equal 0 once we get back to A. Because in the electric field, if we don't change position, even though we move through the circuit, we don't change our position, the change in potential is going to be 0. So the total potential change is 0, one loop through the circuit. And this is conservation of energy. Now, if we look at the equation for the other loop going through EF, we have the same voltage increase across the battery, a decrease across EF, and a decrease across GH, and that's going to equal 0 as well. So that gives us these two equations, the two loops that we have. So you should have one equation for each loop or path that the current can go. So we're going to find the equivalent resistance for this circuit. So we've got two in parallel and one in series with these values, and we have a battery set up in that circuit with a 15-volt power source. And we're going to diagnose the circuit and see that 24 and 48 ohm resistors are in parallel. So we're going to use our parallel equation first. So we'll do 1 over 24 ohms plus 1 over 48 ohms, and that's going to give us a total of 3 over 48 ohms. But notice the unit is in the denominator, so that's important to write the unit so we remember to take the inverse of each side. So we get the equivalent of the parallel section is 16 ohms. And then what we're going to do is redraw the circuit so that we have a singular 16 ohm resistor. Remember, that's what equivalent means, is those two set up in parallels equivalent to the 16 ohms. So now we have these two resistors set up in series. So we're going to use our series equation, which is just adding the two values together, so we get 30 ohms. So the three resistors set up in the circuit are equivalent to one singular 30 ohm resistor. And that's not just in series, that's the overall equivalent resistance in the circuit. And this is important because we'll need this value to calculate some things later on. So let's find the potential difference or the potential drop across each of the resistors in this circuit. So the first thing that we're going to do is we're going to use Kirchhoff's rules. So always write your Kirchhoff's rules. So we know that the current through the 24 ohm resistor plus the current through the 48 ohm resistor, that's going to equal the current that's going through the 14 ohm resistor because it comes back together. That's the junction rule. And that 14 ohm resistor is reading the total current in the circuit and through the battery. So loop rule equation, we have the EMF of the battery, and we know that potential is going to drop across the 24 ohm resistor and then continue along the 14 ohm resistor, and that's going to equal 0. That's one of our loops. The second loop is we have the EMF of the battery minus the potential drop of the 48 ohm minus the potential drop of the 14 ohm, and that equals 0. So the only difference in these equations is the potential drop, either 24 or 48. The other two values are the same. So we're going to use Ohm's law to substitute in and find the value of the total current by looking at our equivalent resistance that we found. So we can find the total current by just doing the potential total in the circuit divided by 30 ohms, which gives us 0.5 amps. So we know that the total current in the circuit is 0.5, which is going through the battery and the 14 ohm resistor. So the 14 ohm resistor has 0.5 amps of current flowing through it. And this is important because it's going to help us find the potential drop. So we can use Ohm's law again to find the potential drop, just doing I times R for the 14 ohm resistor. So I14, that's 0.5 amps, and the resistance is 14 ohms, so that gives us a potential drop of 7 volts. So we know the current and potential drop across the 14 ohm resistor. Now we can use our loop rule equation and substitute values in. We know that the EMF of the battery is 15 volts and the 14 drops 7 volts, so that gives us a total of 8 volts being dropped across the 24 ohm resistor. Well, we know the only difference in the equations was that the potential in the middle was potential of 48 or 24, so those are also going to be equal. So that means the 48 ohm resistor also drops a potential of 8 volts as well. So let's find the current in each of the resistors. So we wrote a junction rule equation back at the beginning, so we're going to use our junction rule equation and bring that back, that the total current is equal to the current through each of the branches. But we have two unknowns, but we can use Ohm's law to help us find the current that's through one of them or both of them. Well, I'm going to choose to use the 24 ohm resistor, which is 8 volts divided by 24 ohms, which gives us 1/3 of an amp or 0.33 amps. So we can substitute the values that we know into our junction rule equation, where the total current is 0.55 and 0.33 amps is through the 24 ohms. So that means the 48 has to have 0.17 amps. We could also use Ohm's law to find it by doing 8 divided by 48, and we get the same value, and then check that 0.33 plus 0.17 does add up to 0.5, so that we know that our junction rule is applying and it works. So we know that the current that's going in each of those branches adds up to the total current in the circuit. Now let's find the value of the power for each. We can just simply use I times delta V. We could use any one of the three power equations. So 8 times 0.33 amps, that's going to give us 2.64 watts. And then we can do the same for each of the other resistors and multiply the current times the potential and get 1.36 watts for the 48 ohm and 3.5 watts for the 14 ohm resistor. So let's recap the problem and look at the steps that we followed. First thing we did is we found the equivalent resistance for the whole circuit. Then we wrote our junction rule equation since we had one junction, and all loop rule equations, which we had two loop rules. Finally, then we found the current in the entire circuit using Ohm's law. That was the current going through the battery as well. Then we found the potential drop of any of the resistors that were in series just using Ohm's law and the total current. Then we used the loop rule equation to find the remaining potential drops across the parallel branch. Then we used Ohm's law to find the current through a resistor. And then the junction rule we used to find the current through the remaining resistors. Lastly, we found the power or the brightness of each bulb for each resistor using delta V times I for each of the individual resistors. Now let's look at an example problem more qualitative. So we have this circuit with a switch, and we have three identical bulbs. That's key, is that they're all identical. So we've got one bulb that's in series, that's going to be labeled A, and we have two that are in parallel, we'll label those B and C. Bulb C has a switch open and no current is initially flowing through it. So what we want to answer is what will happen to the brightness of bulbs A and B when the switch is closed. So I'm going to give you the answer and then we'll explain. When we close the switch, A gets brighter and B actually gets dimmer. So why does that happen? Well, if you remember when we talked about electrical power initially, power is the measure of brightness for the bulbs and it's current times potential difference. So we have to address one or both of those values. So if we're going to address first the current value, with the switches open, we're going to find the equivalent resistance because we have a series circuit. So if each value is R for the resistors, then the equivalent resistance with the switch open is just 2R because it's like C doesn't even exist. But when the switch is closed, then we found the equivalent resistance in the parallel branch first, since B and C are in parallel. So we use our equation for parallel, and we know that each of those has a value of R, so it's going to give us 2 over R. Then we have to flip it, so that gives us R over 2 is the equivalent resistance for the BC branch. And then we can add that with our value for A, which is going to give us R plus R over 2, which is 3R over 2, or 1.5R. So if we compare, when the switch was open, the equivalent resistance was 2R. When the switch was closed, the equivalent resistance was 3R divided by 2. So if we look at Ohm's law, in our equation, if the equivalent resistance decreases, then we know that the current is going to increase. And in our power equation, if current increases, that means brightness increases. But we can also address the potential difference. So if the current increases for an individual resistor with the same value, that means the potential drop is going to increase. So that means if the current increased through A, now it has the same resistance value, the potential is going to increase, which means the power increases even more with more current and more potential drop. So that's why A has an increase in brightness, is an increase in current and a potential drop. So let's explain why bulb B gets dimmer. The current going through A increases, but it's not doubled. So when the current splits to go through B and C, it's going to actually split evenly. So B is going to get less current than it did before. The current is going to decrease. That means the power output is going to decrease. So that explains in terms of current why it's dimmer. In Ohm's law, if we decrease current, that also decreases the change in potential with the same resistor for B. So delta V decreases, so the power is going to decrease even more, which is why B gets dimmer. So let's look at an example with a battery that has an internal resistance. We're just going to do this qualitatively. So the way you'd represent a battery in a simple circuit like this with an internal resistance is you'd set up a resistor and put a dashed box around the battery and resistor to represent that the battery has an internal resistance. Now, generally speaking, the resistance of the resistor is much greater than the resistance of the battery, which is what the double greater than sign means, is much greater. So it's basically that there's negligible resistance. In this case, a battery with significant internal resistance, we have to take into account the resistance. So we're going to write a loop rule equation. So the EMF of the battery minus the potential drop through the battery because it has an equivalent resistance, and we know that it's in series, so the current's going to be the same all throughout the circuit. So we can subtract using Ohm's law, this I times R, and that's the internal resistance of the battery, minus I times R of the resistor, and we know that's going to equal 0. So now we're going to rearrange and solve that equation for the internal resistance of our battery, and we can use our algebra to solve for R, which is going to be the EMF of the battery divided by the current plus the equivalent resistance of the entire circuit, and that would help us find the resistance of a battery that has internal resistance. So this is an introduction to DC circuits. I hope this was helpful, and I hope you have a great day and even better tomorrow.
If you found this video helpful, click the like button down below, subscribe to my channel, Cabby Coaches, and follow me on Instagram and X @CabbyCoaches.